certain topics are there. Okay. Uh, few numerical questions, okay, that I understand. Just tell me the topic also, so that I'll have an idea. According to that, I'll take out time for the doubt class. Okay. Just type the topics. Okay, class. So, coming to what we have studied yesterday, let us quickly complete this portion, and so that by the next week we are at least on hydrostatics. Your extra classes will be put. Let the 12th class, a few extra classes of 12th has been actually put because they have their boards, pre-boards approaching. So just wait for a while. Let that few extra classes are there. Once those classes are over, then I'll put your extra classes also. Firstly, Jesleen, Jobita, Shaima, Ali, Zainab, open the video. This is a rule and please follow it by yourself. I repeat in every class. Now, in the last class, yesterday we studied about surface tension. So what was the surface tension? What was the formula of surface tension?
S by L.
F by L. Yes, surface tension is a property by which the free surface of the liquid tries to stretch itself as if it's a free membrane, and it tries to occupy less area. Okay, that's why it is stretching, so that lesser area of the fluid could be occupied. So examples also we have seen, and the formula as rightly mentioned by Zainab, it is force per unit length. So SI unit is also Newton per meters. Yes, Jessie. Then we saw the concept that doing this task, there is an involvement of work done against the surface tension. That is the surface energy. So work done's formula, what was the work done's formula? The last derivation which we did and we stopped at that. What was work done's formula? Correct, Jesseline. Surface tension into the area. Very good. And if the length, if this is the formula, then what is the formula for the soap bubble? Is it the same or any difference is there? It's for soap bubble. Yeah, this is for the surface energy. In the surface tension, Jesseline, this is right. For work done, we'll say surface tension into 2 times the area, right? And yes, Shaima, twice the length, correct. Correct answer, Shaima. Force by twice the length. You will just double the length, and when you have the area, you will just double the area. Okay. So let's see a question based on this. We didn't practice any question. This derivation was there. Yeah. So this says that, again, I'm saying, everyone, just make arrangements for the camera if you have not arranged for it. So this question says that calculate work done in blowing a soap bubble. So now it's a soap bubble. So we have to have in mind that we have to double the area length, whatever is asked. From radius 2 centimeters to radius 3 centimeters. And you have to find out what's the surface tension is given. You just have to find out the work done. So we know that the work done, when we are referring work done, what is this work done? This is basically this has been answered already, that this work done is the surface tension into area. So surface tension is already given, correct? So when we are referring to the work done, what will be the change in area first? Let us calculate that separately. Because when you are calculating for the for the change in the area, you will just, now at then you can just multiply it with the surface tension. So change in the area will be twice. What's the area for a sphere? 4 pi r square. So 4 pi r2 square means final minus initial 4 pi r1 square. Okay. So this is the change in area. So this will be, if we take 8 pi common, we'll be left with 3 square minus 2 square. No need to convert because everything is given in the CGS unit. Okay. So the change in the area will be 40 pi centimeter square. And what is the surface tension given? 30 dyne per centimeter. So when you are calculating the work done here, you will simply multiply. So this will be 40 pi into 30. So work done will be 1200 pi. Now what should be the unit? What should I put the unit? Someone has answered dyne centimeter. Okay. Dyne for the force and centimeter is for the length. So no. Dyne by centimeter you're just taking. What is that called? That who has just recently answered this joule one. Joule, should we use joule here? Joule per meter square. It's given in CGS, ERG. This is the answer. Joule is in your SI unit, okay? Write it. One more question we'll see based on this topic before we start with X expression. Please write. Yeah, is anything not visible by the way in the screen? I think the question and the solution must be visible. All have completed? Okay, let's see one more question. So this says that if a number of little droplets of water, now number is given as 27, of surface tension sigma, the symbol is just changed, this is written as sigma over here, all of same radius, small r, it combines to form a bigger radius that is having the radius r. Big droplet having radius r means these small 27 droplets are present. Okay, all these are the small droplets. Radius of them is small r. Okay, they are combining here and forming a big droplet whose radius is capital R. This is what is given. Okay, and energy released is converted into kinetic energy, means whatever is the work done, which we mentioned, which we have been studying, this is converted into the kinetic energy. Find the velocity acquired by the bigger drop, because if kinetic energy is present, so you will have motion, some sort of motion in your system. That's why the work done is not being converted into potential energy or another sort of energy. It is being converted into the kinetic energy. So if you have the kinetic energy being present, so there must be a velocity. So firstly, let us find a relation between the small radius and the capital radius. So one thing, even if these 27 droplets are combining to form one bigger droplet, which quantity do you think will remain the same? Okay, think it the opposite way. You have a big one drop. You are cutting it into 27 drops. Which quantity will remain the same? Yes, Ali, your answer is right. Zainab, the question is, small droplets are there. These small 27 small droplets are present. And we have combined it, coalesced it, stuck, all these drops are stuck, and one big drop is formed. Which physical quantity would remain the same? See, radius won't be the same. Small radius is different, capital radius, capital R is different, big radius is different. So which quantity will be the same? If you want the answer, a hint can be take the bigger droplet first and break it into smaller droplet. Now think which physical quantity will be the same. See, obviously radius will be broken down into smaller radius, but one quantity will be the same. Okay, think it in this way. You have a bar of chocolate, okay? And this entire bar of chocolate is fit into a box. This is fitted into a box. Now what you did, you broke all of these lines together, means you had these small squares with you, all these with you. And then you're putting it back into the box and you're seeing that it is completely fitting it despite breaking it. Why? Which quantity is remaining the same? Will it happen if I have a bar of chocolate? Chocolate has the packet of it, the box of the chocolate is there, and I had this chocolate. I just took out the chocolate, I broke it into the pieces, and still when I joined it and put it back, I was able to do it. See, length would definitely change. Suppose length was this, so now these will be some L dash, small length. So length is changed. But which quantity is the same that it is being fit completely back? Area is two dimension. Those who are answering area, two students have answered area. Area is 2D, chocolate, sphere. Do you think these acquire? This is not a plain sheet of paper that will be acquiring the surface area. Which quantity is it? It's not a two-dimensional thing. A chocolate, a piece of chocolate, a small cube of chocolate, or a sphere, cubes, these are three-dimensional figures. So if you have thought till here, what just add one more dimension and answer. Ali's answer was absolutely correct at the first place before even giving the example. Volume. Volume is the same, no? That's why this is acquiring the same portion. Volume, not the area. See, okay, in layman terms, you can say same area is there. So same area is being occupied, which was taken. But area is a two-dimensional quantity. So here volume will be the same. Okay, so volume is the same in this case. So it means 27 volume of these smaller drops, means volume of one small drop into 27 is actually equal to the volume of one big drop. So what is the volume of a sphere? 4 by 3 pi r cube. So 27 into 4 by 3 pi small r cube. This is equal to 1 into 1 big drop into 4 by 3 pi capital R cube. 4 by 3 cancels, 4 by 3 cancels. 3 into small r is equal to capital R. So you can say the smaller radius is capital radius by 3. Tell me till here is clear. Now you at least have the relation. Now you have to calculate the work done. What will be the work done? Work done will be the surface tension into 27 times the 4 pi small r square. You're calculating the area. So area of small spheres, right? This is for the smaller ones. And for the bigger droplet, it will be just simply 4 pi r square. Surface area of a sphere is like this. And since 27 spheres were there, that's why I multiplied 27 here. Okay, so this surface tension into 27 4 pi r square minus 4 pi capital R square is equal to half mv square. Surface tension, the symbol is used as sigma. So 27 4 pi r square minus 4 pi capital R square is equal to half mv square. What is the velocity? From here you can calculate in terms of capital R. Why? Because small r, you can get your answers and give your answers in this term now. Why half mv square? Because the work done is changed into kinetic energy, and kinetic energy has the formula half mv square. Okay, write down this question. Done. Okay, class. Now the concept of excess pressure. So excess pressure basically means, see, there are two types of pressures which exist. First, before we go on to the excess pressure, understand what all pressures are acting when we have a film or the surface which is present. Okay, so this flat part which you see when you suppose take a plain glass, fill it with water, you will see the surface is flat. So this edge of the surface, this is called as the meniscus. The free plane surface is called as the meniscus. Okay, in chemistry also you must have used this term meniscus. So if you see this is flat, we call this as the plane meniscus. So the pressure from the liquid is the pressure from, this is the PL, this is represented as PL, means the pressure by the liquid, and another pressure is pressure by the vapor, whatever air, whatever is the medium present above. This, whatever is this here. So if this is a flat meniscus, means both are balancing each other well. That's why only the upward pressure and downward pressure both are exactly the same being balanced, and you're getting a flat surface, right? Then the second concept is, if you're getting a bulged part, if you see you're getting a bulged part, this is called as a convex meniscus. In class 12th, you will understand this convex concave concept better when you will have the ray optics in your syllabus. Right now, just understand, if you see bulged part, it is convex meniscus. So see, vapor pressure is acting. Pressure exerted by the liquid is also there. But see, the liquid's pressure is more, that's why it is pushing it upwards. So here the liquid's pressure is more than the vapor. If you see a cavity, a concavity is present, then this is called as the concave meniscus. So here also the pressure by the vapor is there, pressure by the liquid is there, but the vapor pressure is more, so it is depressing it. So that's why we have the vapor pressure more than the liquid's pressure. Before we start with excess pressure, just quickly write down this slide. Vapor pressure, Shaima. That's vapor pressure. Vapor pressure, pressure by liquid. Done by now, all of you? Completed? Okay, I think now by now all of you must have completed. So what is the excess pressure? See, this is a bubble which has been drawn. Excess pressure is basically the net pressure that acts on a bubble. So see, if air bubble is there in a liquid, there will be atmospheric pressure also acting on it, right? This is the pressure from the atmosphere. Atmospheric pressure is also acting on it. Let's say the radius is r. Radius is r. From inside, there is a pressure by the liquid also. That is the inside pressure which is present. This is just a sphere. Okay, sphere of bubble is there. This is it. So excess pressure is basically the net pressure which is acting outwards. So if we are taking the net pressure which is acting outwards, means inside's pressure which is acting minus this atmospheric pressure. P inside minus the pressure atmospheric. So yeah, I've written it here also that net outwards pressure is P. Radius of the drop is R. Surface area of the drop will be pi R square. Okay, the surface area of the drop is pi R square. So class, what will be the pressure? See, pressure, let's say the excess pressure is P. Surface area also I'm writing it as 4 pi R square. Okay. Now tell me, or it is capital R. I've taken. Now I have written this. Can anyone tell me? This is for a single air bubble, correct? Just one single air bubble. Because you also won't get a question on complete fluid, right? Okay. Okay. Yes. So yes, class, this is the pressure which is given. This is the area of the soap bubble. What will be the pressure? What will be the force? What will be the force here? Correct, Shaima. Not mg. Pressure is given, area is given. Pressure is force by area, so force will be pressure multiplied to area. Pressure into 4 pi r square. So this is the force which is present. Yes, Ali, your answer was right, F into A. Now, work done due to the excess pressure to expand the drop by some small amount dr. We are taking some very small amount dr to expand it. We are calculating the work done. So basically, what exactly is this? Let's say the work done surface change, surface area change is this. This is it. This is the soap bubble, and this is just to see how much a bubble would expand. So this much of this much of area to be expanded, and this is dr, very small amount, that is dr. Okay, so when we are calculating work done, it will be surface tension into area. What will be the area now? Final minus initial, we write. We always write final minus initial. If dr is there, already the radius is r. So for this is the final state. So what will be the total radius? See, finally the drop will look like this, r plus dr, total radius. So what will be the surface area? Surface area will be 4 pi capital R plus dr whole square, minus what was the initial area? Initially, the drop was just having the radius r. So this will be 4 pi capital R square. This is the work done. Tell me, all of you, this equation is clear to all of you?
Yes.
Okay. Now, class, we'll just expand this surface tension into 4 pi. Now, r plus dr, take it as an identity, r square plus dr square plus 2r into dr, right? And from here, 4 pi has been taken out, so only minus r square will be left. Let's see, r square minus r square will be cancelled. Why I have written r square? Because 4 pi I have taken outside the bracket. So from here, minus r square will be left. And what is this? This is a plus b whole square's identity. Okay. Now, class, there is one concept that this dr means how much this dr will be, the expansion will be so small in terms of 0.00. This is infinitesimally small. That's why this letter d has been put. That, see, remember in integration and differentiation we have studied that you will whenever you have this d symbol, it means something is very infinitesimally small. So dr, when dr is present, it means the expansion is very less. It has been expanded, but the expansion is very less. So this dr is almost equal to 0. So by this will be equal to 0. Dr square will be equal to 0. Dr square, sorry, dr is so small that its square will almost be equal to 0. We can consider dr. That's why we have taken it. Otherwise, if it was 0, then our answer would straight away have been 4 pi r square minus 4 pi r square, 0. Work done would have been 0 because there wasn't any expansion. But expansion is very less, class. Initial radius is capital R, final radius is R plus dr. But this dr is not so huge that you're going to consider it square. Okay, if it is 0.0001, that is significant. We can consider it. But square of 0.001 will give you such a small number equal to 0. So that's why this dr square, we have written it as 0. Okay, so what will we be left with? This is actually dw because we have taken dr. So this is actually dw only. So dw will be 4 pi. Okay, s into 4 pi. Let me write 4 pi into surface tension multiplied to 2 into 2r into dr. So from here, the work done will be 8 pi s. Okay, this is 8 pi s rdr. rdr. Okay, what is this? Statement of work done. Correct. This is the work done, right? Now, class, if this is the work done which is present, what is the work done in terms of the excess pressure to expand it? See, the work, we are calculating the work done to expand it and find out it. Work done, we've already studied that the normal general formula of work done is force into displacement. Okay, one is this, that it is surface area into change. So work done due to excess of pressure to expand the drop. Force is given. We have calculated the force, right? We have calculated it. Force is equal to P into 4 pi r square. What is the displacement now? dr. You have seen that this soap bubble has expanded to this dr. So what will be the work done? Work done will be force multiplied to the displacement. So it will be P 4 pi r square multiplied to dr, right? This is the force into displacement. So this is your first equation, and now you have obtained your second equation. So both the equations are there. You can equate it. Pressure into 4 pi r square dr is the first equation, is equal to 8 pi s r t r is the second equation. Dr will be cancelled. Pi cancelled. Then 1r is cancelled, and 4 here, this will be 2, right? So from here the excess pressure is equal to 2 is left. From here surface tension is left. From here radius is left. 2s into r, that's it. 2s multiplied to r. And if it's a soap bubble case, if this is excess pressure inside a soap bubble, so this is 4s by r, because we double it. We always double it. Okay. So an air bubble in water or a liquid has only, yeah. See, when we are talking, an air bubble in water or a liquid drop has only one liquid surface with contact. But when you have soap bubble has double surface. This is because it has double surface. From backside also, you see there is one more double film is there. That's why you double it. Now, in case bubbles or liquid drops, in case of bubbles or liquid drops, the pressure on the concave side of liquid air interface is greater than that of the convex side. So the concave side is more, means this is more, the meniscus. Means here you should understand the vapor pressure is basically more than the liquid pressure. Okay. Just one addition into it. Class C, 2s by r is there. Now, if I say this is just a case when the soap bubble was taken, but we never considered this atmospheric pressure. What if the soap bubble is outside? We do not, you have seen those soap bubbles which come in those different molds, and you dip it, and then when you blow it, bubbles come out. All of you must have seen it in parks and all. Yes or no?
Yes, ma'am.
Right. So if it is that case and you're considering it, so you will not just simply write 2s by r. You will add atmospheric pressure also. See, if atmospheric pressure is actually acting, see, atmospheric pressure, excess pressure at atmospheric, the net pressure acting. But if the soap bubble is completely dipped into water, so small expansion will be there. So you can use 2s by r. If it's a soap bubble, you can use 4s by r. But if it is open to atmosphere, then atmospheric pressure will be acting. See, inside this, the pressure will be there and excess pressure will develop. One will be the pressure inside the drop that will be excessively pushing it outside. So now your excess pressure, which we wrote in the starting, which I wrote in the starting, P inside minus P atmosphere. So you will completely make the equation P plus P ATM. What we have calculated, sorry, if you want to find out what is P inside, excess pressure we now know. So P inside, this will be equal to, what is the excess pressure? 2s. This will be plus P plus atmospheric pressure. So this is 2s by r plus the atmospheric pressure P naught. What is the atmospheric pressure's value, class? We did in the first class of fluids. What is the value that you take for atmospheric pressure? Jobita? Wrong answer, Zainab. Correct answer, Shaima. By now, you all should have learned that value. even if you forget that starting 1.01, 10 to the power 5 should have been remembered. Yes, Ali, 10 to the power 5. Atmospheric pressure, it is actually 1.01 into 10 to the power 5 pascals. Will you remember it now? Zainab, Jobita, yes or no? Now, will you remember it when I'll ask you in the next class? Okay, one more thing, class, in this. If one addition can be there that can come in your exam is, okay, as soon as the question is asked, all the network definitely goes off. See, one thing is that if the bubble is here, suppose, now atmospheric pressure is also acting, it is open to atmosphere. Fluid is also there, so there will be inside pressure, that is the excess pressure of the fluid also. But when the fluid liquid column is there, which is having height, then your H rho G will also come. So if you are asked to calculate what is the inside pressure, then your normal pressure would be there. Sorry, your excess pressure would be there, 2S by R. It is open to atmosphere. Your atmospheric pressure will also come, and your H rho G will also come. The pressure exerted by the liquid column will also come. Did you understand all these? See, I'm repeating everything once. Just pay attention and hear. See, excess pressure is the net pressure. Okay, that is acting from inside, outside, whatever is the net pressure that is acting. So we calculated it. We calculated the work done. Work done is pressure into displacement. So force is pressure into area. So pressure into area into displacement, P 4 pi r square dr gave us the work done. Because dr, this is the expansion coming in the fluid. And secondly, when we use the equation of surface energies equation, means surface tension into area, then we got 8 pi s rdr. When we equated both of these, we got P is equal to 2s by r. Tell me, in this first segment, do you have any doubts? Is it clear to everyone?
Yes, ma'am.
Okay, apart from Ali and Zainab, is it clear to the rest of the three, Jobita, Jesleen, Shaima?
Yes, ma'am. Yes, ma'am.
Now, if the question says soap bubble, double the surface area, 2s by r. Clear? This we have discussed. If the bubble is open to atmosphere, atmospheric pressure is somewhere mentioned, a hint about atmospheric pressure is given, then inside pressure is asked many times in the question. Then excess pressure, because you know the excess pressure is the net pressure. Net pressure plus the atmospheric pressure will give you the pressure inside the drop. See, it is equal to the net, it is equal to this. That's why this soap bubble is intact. Otherwise, the inside pressure, if when the inside pressure is more, the bubbles burst out. Okay, so this is inside case. And if this part is clear, why we are adding atmospheric pressure? Because it is open to atmosphere. This part is clear?
Yes, ma'am.
Everyone?
Yes, ma'am. Yes, ma'am.
Okay. And if the soap bubble is present in a liquid which has a height, whereas water column is present, then not only you're going to add the atmospheric pressure for the inside pressure, you are going to add the H rho G, that is the gauge pressure also. The pressure exerted by the liquid column, all these things we discussed in the initial classes. Remember the value of atmospheric pressure. Tell me, class, till here now everything is clear to all of you?
Yes, ma'am. Yes, ma'am.
Jesleen, Jobita?
Yes, ma'am.
Okay. Okay, all of you, write it. This is an important section. Please start writing from.
Ma'am, can you scroll up?
P is equal to P. Means I was just writing that pressure that is it we have taken is P and area is 4 pi r square. So this is not rho, this is P. Should I scroll, class?
Yes, ma'am.
S, surface tension class. Not rho, surface tension. Written this last line.
Yes, ma'am.
Have you all written this page?
Yes, ma'am.
All of you?
No, ma'am.
Okay, write it. Written.
Yes, ma'am. Ma'am, can you scroll up?
Done, everyone? See, this question says that the lower end of the capillary tube of diameter 2 millimeters, this is dipped in See, let me show the question first. The lower end of the capillary tube of diameter 2 millimeter is dipped 8 centimeters below the surface of water in the beaker. We have to find what is the pressure required in the tube to blow a hemispherical bubble at its end in water. See, surface tension is given and you have to find the excess pressure also. Basically, this is the figure which is already given. This is the bubble. What is the pressure required? So see, we have studied this is a liquid container. It has already mentioned that this is required in a tube. So it means the pressure will be exerted from the liquid also. So we have just now seen 2S by R plus P naught plus H rho G. So let's see, do we have all the values? 2 into surface tension. Yes, it is 7.3 into 10 to the power minus 3. By the radius is given as 8 centimeters. Diameter is given as 2 millimeters. So radius will be 1 millimeter, which is 10 to the power minus 3 meters. So this will be 10 to the power minus 3 plus atmospheric pressure 10 to the power 5. Height is given, yes, 8 centimeters. So this will be 0.08 meters into density of water 10 to the power 3, acceleration due to gravity 10. Calculate and tell me what's the value coming. Write down this question. This completes with the topic excess pressure. Now we are just left with capillarity. That's not a very big topic. Capillarity from this hydrostatics. And in the next week only, we are going to start with hydrodynamics. Okay, then these portions will be left. Okay, class, if you all have completed writing, tell me whatever is the answer in the next class. You all can leave. Please revise and submit the homeworks. None of you have submitted from this chapter. Jobita, you have also submitted from the NEET portion, and just last homework was done from the earliest topic. Everyone, please submit the homework so that we can discuss it. All right, please revise and come. Okay, any queries, let me know. Shaima, just text the team also Learnivio's number. On the Learnivio's number, just tell them this much hours class you need. Just total number of hours, whether it's 2 hours, 3 hours, they'll arrange it. Okay, Shaima?
Okay, ma'am.
All right. Okay, class then. Thank you so much. As soon as you'll be completing, you can start leaving.